palestra abordará o tema Embalagens plásticas para Fresh Produce e a sua contribuição para a segurança alimentar e redução da fome no mundo, com o Dr. Jeffrey Brecht. Dr. Jeffrey é diretor do Centro de Distribuição de Alimentos e Varejo da Universidade da Flórida, professor PhD e especialista em extensão pós-colheita com atuação em todo o estado da Flórida, onde leciona o curso Princípios da Horticultura Pós-Colheita. Ele é autor de mais de 300 publicações técnicas, incluindo cerca de 130 trabalhos publicados em periódicos. Iniciou como membro da Sociedade Norte-Americana para a Ciência Horticultural em 2006. Então, com vocês, Dr. Jeffrey.
I'd like to start by thanking Alfredo Schmidt, the visionary who started and organized this conference, for inviting me here. It's a pleasure to be here. I also want to mention the staff that he has working with him, especially Samara Souza, who made all the arrangements for me, made everything a pleasure. I wish I could be making this presentation to you in Portuguese, but unfortunately I only know English, so if you'll bear with me, the slides are in Portuguese and I have my English printout in front of me. The program today is amazingly varied, talking about food and medicine and many other subjects. I think it's appropriate that we start with food, the first requirement that we have for leading a healthy and happy life. It all starts with agriculture, growing our food. My specialty is how the food gets from the farm to the consumers into our homes and restaurants and other institutions for us to eat. At the University of Florida, I lead a group of colleagues who do research in the distribution of food. It's called the Center for Food Distribution and Retailing. We work with the industry on the technology that's related to the food being distributed worldwide and the science behind that. I personally am in horticultural sciences, which is fruits and vegetables, so I'm going to focus on that for my talk because that's where I have the most experience and knowledge. So let me get started. Packaging for food has 4 functions. It provides protection of the contents. It promotes shelf life extension so that the food retains its quality and nutritional value as it moves through the distribution system. There's a convenience factor. We want the food to be packaged in a form that makes it convenient for consumers to purchase and use it. And it also has a communication function. The labeling on packages is how we communicate to the customers what is inside, what are the features, what are the qualities of the food. Oops. There are different levels of packaging. The first level is the consumer package. This is what the consumer takes into their home. The second level is a container that's a convenient size for handling at the beginning and the end of the distribution system. And the third level is a unitized pallet, which is the way the food is handled during the distribution system as a large unit. And there's uses of plastic at all 3 of these levels. In fact, it's integral to how fresh food is handled in the distribution system. We have protection from injury. Fresh fruits and vegetables are very delicate, actually. They can be easily injured. And because they're living, when they're injured, they have an injury response, different things that you see, the bruises that develop. It also has effects on the nutritional value and the appearance of the product. The packaging also protects the food from the ambient environment. So it's protecting it from the conditions outside that tend to promote the degradation of the food quality and food value. Among these are temperature. That's the most important thing. We're trying to lower the temperature and maintain a low temperature for maintaining quality during distribution. And packaging, in some cases, especially insulated packaging, can protect the food from temperature fluctuations outside. There's also other things like potentially protection from light. Humidity protection is a very important thing because fresh produce and other fresh foods tend to lose water, which degrades their quality. And plastic packaging is really the optimal material for reducing that kind of deterioration. Oxygen is another factor in the outside environment that has negative effects on food. It causes oxidation chemical reactions that degrade the food quality. It also promotes the respiration and metabolism of fruits and vegetables so that they age more quickly. So protection from oxygen is something that's important, and I'm going to spend a fair amount of time in my presentation talking about that area. It's the area that I personally do research in. So, as I mentioned, plastic packaging is the best option for minimizing water loss during distribution, and you see some examples of it here. Liners within the cartons, individually wrapped heads of lettuce. You see it in all sorts of fresh produce that the plastic packaging is there, and a major purpose of that is to reduce water loss. Another important consideration is that the packaging actually has to be compatible with the distribution system. So it carries the product from the farm, from the field, all the way to the retail level and into the consumer's home. And it has to be appropriate. It has to be designed to fit into that system at all the steps. It has to be compatible with the handling system. Individual types of fruits and vegetables and other foods all have their unique particular procedures that are followed for handling them, packing, grading, transporting, how the product is cooled to lower the temperature. Those are all unique, and the packaging has to fit into that system. For produce cooling, as an example, two common ways in which the heat is removed from the produce to bring the temperature down to an optimal low level is by what's called forced air cooling on the left. And this is a system where the refrigerated cold room air is drawn through the packages so it flows directly across the food product to pick up heat and remove that heat, and then it's cooled again and ejected back out into the room. And so the package has to be designed with venting that allows that airflow in the direction that you want. The other common cooling method is hydrocooling. Oops. And this is an example of what's called a shower hydrocooler, where cold water is showered over the top of the produce. And you see here's a plastic container that is very open, that allows the water to move through the product from one layer of containers to the next, all the way through very easily and efficiently. The packaging has to be compatible with the system of distribution. So food is shipped within a country, between countries, between continents. You have truck, you have train, you have ocean-going vessels, you have air transport. They all need unique packages. And just as an example, I'm going to contrast the way food is distributed by ocean versus by road or over land. In a truck container, there's a refrigeration unit which is distributing cold air. These were originally designed for frozen food, so the idea is that the air, the cold air which comes out the top, it would go the length of the truck trailer and circulate like a cold envelope around the frozen food to shield it from the outside environment. And with produce, when that system is adapted for produce, the packaging has to be vented so that the air can, oh, come on. The air can actually move from the rear of the trailer through the product back to the front. In contrast, in ocean-going vessels, in marine containers, they reverse the airflow. And in this case, the cold refrigerated air comes from the bottom and goes under a false floor and then moves vertically from bottom to top through the load. And they do that by this bulkhead, which is a false wall in the front. It forces the air to come out the bottom. It goes the length of the container and returns through the top. So in this case, the venting has to be vertical, whereas in the other case, it has to be horizontal. And there's many examples of this where the produce packaging has to fit the system. And the interesting thing about plastics is that they're really becoming more and more common. This is a revolution in food distribution that's been going on for about a decade, and that's the replacement of paper fiberboard cartons with returnable plastic containers. And one of the great advantages of these is that they can have extensive venting for that air movement, allowing temperature control while retaining much greater strength than the paper containers. And it's also a green technology. You get reductions in the total energy that's invested in the system. There's 95% less solid waste because the material itself is not only reusable, the returnable part of the name, but it's also recyclable at the end of its life and can be used to create new RPCs. You have 29% reduction estimated in total greenhouse gas emissions. This is comparing the returnable plastic container, or RPC, to corrugated containers. So there's a lot of advantages to that, and it's being used more and more for the handling of food products, perishable foods. At the consumer package level, if you have noticed this, you're all in the plastics arena, so you probably are more aware and have noticed this more than the typical consumer. But almost everything that we buy at the consumer level is in plastic packaging. And the reason for that is because of the advantages, as I mentioned before, in terms of reducing water loss from the product. Also, you can have great clarity so that the consumer can see the food inside the packaging. It also relates to controlling the movement of oxygen and carbon dioxide in and out of the package, which is what I'll be talking about more in a few minutes. So there's rigid types of packages. There's flexible types of packages. One of the types of packages that we've done research on recently is this type of a container. We call it a clamshell in English, opens and closes like a clamshell. But this has an individual pocket for each fruit that suspends the fruit in the package so that it touches neither the bottom or the top and actually can move up and down with vibration during transit. And this is a way that we think that allows riper fruit to be shipped and brought to the market without being injured. Therefore, consumers are going to have a better quality product than what's often available now, especially with very long distance shipping, where the tendency is to pick the fruit very green to have it stay hard so that it will still be intact when it reaches the destination. So these are just more examples of consumer packages, and this is fresh cut. Fresh cut or minimally processed foods have really grown over the last 15 to 20 years in the United States, and I've seen them here in Brazil quite extensively. These packages, you may not realize it, but they're all made with semi-permeable plastic materials to control the oxygen and carbon dioxide level within the package. And this is critical. There would not be a minimally processed food industry without this kind of plastic packaging, because once you cut the product, you've wounded it, it's still alive, it responds with a wound response that accelerates the metabolism and the deterioration, and typically you can't get this kind of product through the distribution system without having this kind of plastic packaging. So the whole industry is predicated on the existence of plastics that can be used for that purpose. Even when we are seeing food still being shipped in corrugated containers, always you see that inside that there's some kind of plastic packaging. It can be the clamshell type rigid containers that I mentioned. It can also be plastic liners in the carton to reduce the water loss, or individual wrapping of the fruits or vegetables. There's a lot of different considerations that go into deciding exactly what the correct and best material is for this type of packaging. It includes the tensile properties of the plastic, the tear strength of the film, impact strength of the rigid material, heat seal strength. These modified atmosphere packages, what they're called for the fresh cut, they have to be sealed by a heat seal process, water vapor transmission, gas permeability, as I mentioned, min-max temperature resistance or applicability to different temperatures. You don't want something that at a low temperature that's optimum for the food becomes brittle or cracks, and stress crack resistance. All of these have to be considered in developing the package. Okay, as I said earlier, I'm going to spend some time talking about this area of modified atmosphere packaging. I think it's quite interesting. I hope that you'll agree after I've talked about it some more. So the fruits and vegetables are living organisms. They breathe. The respiration process in plants is the same as for animals, including humans. The biochemical pathway is the same with the same reactions. So they take in oxygen, they give off carbon dioxide. And the basis of modified atmosphere packaging is that you take advantage of that respiration rate of the food product in concert with the semi-permeable plastic packaging. And the way that you restrict the gas diffusion to create a modified atmosphere is either with semi-permeable films, like I mentioned. There's also microporous films where there are actual physical holes through the plastic. Because these are very highly permeable, it's possible to have a rigid, impermeable package with just a small patch of microporous material acting like a window for the gases to move in and out. And then finally, for very high respiring products, it's sometimes necessary to make physical perforations in the package. And then these packages, as you can imagine, can be combinations of all of these things. So, MAP, modified atmosphere packaging, is referred to as MAP. How does it work? You match the product respiration rate with the package permeability to achieve a desired atmosphere. Fruits and vegetables are quite resistant to low oxygen and elevated CO2, much more than us. The normal oxygen level in the air is 20.8%. If it reaches 15 or 16%, humans will pass out. and you'll die if it goes below that. But fruits and vegetables actually do very well as low as 1 to 5% oxygen. Because their respiration is based on oxygen consumption, if you lower the oxygen, it slows the respiration, which slows the metabolism, and it slows all the negative changes related to the quality and nutritional value that happens over time after fruit and vegetables are harvested. So you're looking for a package that equilibrates in that range of 1 to 5% oxygen, 0 to 20% CO2. There's a wide range of tolerance of CO2 among the products, but if you can get above 10%, it's very good for reducing microbial growth on the food, because the microorganisms are more sensitive to carbon dioxide than the plant material. And of course also water vapor is a third gas that has to be considered, so the package also has to be designed for retaining the water vapor. But with fluctuating temperatures, you can have problems with condensation of water on the inner surface of the package, which means you can no longer see through the film to see the product. So there's special treatments that are done to reduce that condensation. So this illustrates what's happening. The fruit is giving off CO2, it's taking in oxygen. If you can enclose it in a package with restricted permeability, the CO2 is going to increase and the oxygen is going to decrease until it reaches a steady state, and that means that the respiration rate has been inhibited until it matches the permeability properties of the film, and so you have equal amounts and it comes to a steady state or equilibrium and the gases start changing. So the package has to be designed to reach that optimum combination, which is different for each type of fruit and vegetable. Just as an aside, interestingly, MAP is also widely used for meats and seafood. These are still fresh foods, but they're not living, they're not respiring like the produce. So the MAP in this case is strictly working on chemical reactions in the meat and seafood. So the main challenge with meats is to retain red color at the same time that you retard microbial growth of spoilage bacteria primarily. So we use barrier films that can maintain 60 to 80% oxygen in order to maintain the oxymyoglobin in a red color state. If it's oxidized, it turns brown, which is very unappealing to consumers. And then it's combined with 20 to 40% carbon dioxide to inhibit the bacteria. In the case of seafood, there is a different purpose that has to be achieved. Primarily, we're talking about inhibiting the microorganisms that can degrade the flesh, and those may or may not require oxygen. So depending on what the common spoilage organisms are for the type of seafood that you're dealing with, you may want higher or lower oxygen. Fatty fish become rancid in the presence of oxygen. So in that case, with those type of fish products, you need to have very low oxygen. So typically you're using a barrier film for MAP for seafood that maintains 20 to 50% carbon dioxide, and then the remainder of the atmosphere is oxygen or nitrogen according to what the type of seafood is. So for some of the principles of MAP, the respiration rate of the fruits and vegetables involves equal consumption of oxygen and production of carbon dioxide. That's the RQ, or respiratory quotient. It's about 1. The film permeabilities can vary quite a bit. It's one of the selection factors that you have. Quite often for the semi-permeable films, that ratio of CO2 transmission to oxygen transmission is 4 to 6. And for perforations, it's just, this is diffusion through the air, so it's based on the weight of the two molecules. So the ratio of CO2 to oxygen diffusion rate is about 0.8. And so what that means in practice is when you choose a film or a perforation or a combination to get different beta ratios, which is that ratio of gas permeability, you can achieve different combinations of oxygen and CO2. So if you have a beta ratio of 4, the combinations of oxygen and CO2 that you can achieve fall along this line, whereas if it's 2, they would follow along this line. If it's 1, they would follow along this line. So you can see there's an infinite possibility of combinations to achieve whatever the atmosphere is that you want. Another consideration is how you achieve the atmosphere initially. As you might imagine, it's beneficial to achieve the atmosphere that's optimum for the food as quickly as possible. And so for that, you use what's called active map. On the other hand, passive map would be allowing the respiration rate to, over time, generate the atmosphere and reach the steady state. Or you can get it right away by flushing the package as it's being sealed with the combination of nitrogen, oxygen, and CO2 that you expect to achieve at the equilibrium state. And this illustrates how that looks in practice. If you just put the produce inside a semi-permeable package, it may literally take days for the steady state to be reached. The scale here is 0 to 16 days. But if you flush it, then obviously you have that equilibrium concentration immediately as soon as the package is formed. And that can be very beneficial, especially for very perishable product like those minimally processed fruits and vegetables. So you have choices of all sorts of different films. These are some of the films that are commonly used for different types of food packaging. Low-density polyethylene is sort of the basis for a lot of MAP film packages, using EVA, polypropylene. PVC is typically the type of film that's used for the stretch clear film that you see quite often in grocery stores, clear plastic that's stretched over a tray of some kind, usually a styrofoam tray. That's primarily being used for its lack of permeability to water vapor. So it's not really creating modified oxygen and carbon dioxide, but it does retain water very well. You can have monolayer films, which are really not that commonly used. So you have one polymer, one resin, one film. More commonly, you have blended films or multi-layer films. If you blend different plastics together into a film, you can get another whole range of permeabilities because the permeability of the film is going to become a weighted average of the permeability of each of the polymers that were blended. Or you can have multi-layer films. This is probably the most common for fruit and vegetable packaging because the different layers can serve different purposes. Oftentimes the outermost layer is primarily chosen for how well it's adopted for printing for the label on the surface of the film, for example. And those can be either co-extruded or laminated, just a choice in the process to make them. Metallocene films are becoming more and more commonly used for modified atmosphere packaging. You get reduced variability. They tend to be over a given area more constant in their permeability. You get better control of film density. The sealing characteristics are good. You get the nice, good clarity and sealing characteristics. So those are really becoming more popular for MAP packaging. So this is just a couple of examples of how you can use a different type of packaging to get different atmospheres. If you have a film that has an overall beta ratio in the range of 4 to 6, that means that the CO2 is going to move through the film 4 to 6 times faster than the oxygen moves through the film. If the respiratory quotient, as I mentioned, for the produce is 1, like I said, that means you're going to potentially be able to get an atmosphere, say, 4% oxygen and 3% CO2. So the oxygen comes down from 20.8% much more than the CO2 comes up from almost zero to start with. And there's a lot of film-based packages like that. One of the most commonly used for strawberries, for example, is actually used at the entire pallet level, where this pallet cover is actually a modified atmosphere package that's used during transportation. And what they do is they put it over the top, they seal it with tape at the bottom, they put in a nozzle that draws a small vacuum and replace that with CO2 to have an active modified atmosphere package with high CO2 primarily to control decay, and then that goes through the distribution system. As I mentioned, all of the fresh cut or minimally processed products that you see, essentially all of those are in a modified atmosphere plastic package. The other approach is to use microperforated map systems. This picture just shows large macro perforations so you can see, but actually in practice they're very small, 40 to 20 microns in diameter, created primarily by laser because that gives you the most uniform shape and size of the perforations. And those type of films, because they have a beta ratio of 1, that's like about 1, like the respiratory quotient, allow you to get higher CO2 for the same oxygen. So with a perforated package, you could get for this same 4% oxygen, you could have 15% CO2. So as I say, there's an infinite number of possibilities for that. And as I mentioned before, these can be combination packages as well. Thank you, you're saving me. So you can have a package that relies exclusively on the perforations, or you can have a combination of a semi-permeable film and a perforation and anything in between that you can imagine. Some examples of those type of microporous packages. You can see here in this case you can't see any holes. One of the things that you can notice sometimes is that the porosity is achieved by embedding some kind of material into the film. And this can be diatomaceous earth or other small particles. And the effect is that you get sort of a cloudy appearance to the film. So these exist, but they're not terribly popular because of this cosmetic reason. But there are other microporous films that are very clear and have nice properties in that regard. Now, I mentioned early in my talk that temperature is really the most important environmental factor for maintaining the quality and the nutritional value of foods. And it has an interesting interaction with the modified atmosphere packaging. And that's because the produce respiration rate or metabolism rate is very closely tied to temperature. And in fact, the respiration rate changes 2 to 4-fold for every 10-degree change in temperature. But the permeability of the plastics doesn't change that much. So what that means is when these packages are designed, they not only have to be designed for the specific food product, but they have to be designed for a very narrow temperature range, and then through the distribution system, that temperature range has to be maintained, because if the product goes out of the range, then the atmosphere will change. And if the temperature rises and the respiration rate increases until there's a lack of oxygen, then the fruit or the vegetable will transition to fermentative metabolism and start producing ethanol and acetaldehyde, and then the product will spoil that way. So the typical solutions to that is, in some cases, just design the package for a compromised temperature. Like with the minimally processed products, most of them are best kept near 0 degrees, but when they're put on display in the grocery store, they're not at 0 degrees. In fact, they can be as high as 15 degrees. So many of these companies that make these kind of products, they design the map for a in-between temperature of about 7 degrees. So they don't get as much benefit of the map at the low proper temperature that's normally during distribution, but they don't reach the fermentative stage at the higher temperatures of display in the retail level. The other way to do it is like that pallet map system, which is only designed for the distribution segment, and it's taken off before the product goes to the store, so therefore it doesn't run into that temperature difference, and it's only designed for one segment of the distribution chain. Another approach that is coming along, it's really quite fascinating, is to actually make polymers that have varied side chain length so that they transition between a solid phase and a liquid phase at a desired temperature. And when they change from solid to liquid, the permeability increases greatly. So it's like opening a window, or like having two different packages, one for a lower temperature and a different one for a higher temperature. This is a commercial package that's very common in the US now. It uses a microporous patch, like I mentioned before, as a possibility. There's a patch on a plastic bag of minimally processed produce. It's coated with a gel that is this temperature responsive polymer, and then that changes phase and allows a change in permeability between a lower temperature and a higher temperature above and below the phase change temperature. Some research that was done at the University of Florida in materials engineering. This is actually a Brazilian PhD student working at the University of Florida. He's developed a film that compared to the normal films, the responsiveness to temperature is much greater, and it can be created so that it mimics the respiratory, the temperature responsiveness of the respiration rate of the product. That has not been commercialized yet. It's not a very strong film, so it has to be between two stronger layers of film. So a few more examples. Microwavable packages, if you've ever seen these. This is another twist on modified atmosphere packaging, but it also is adaptable to microwaving. The food is actually cooked by the steam that's formed and trapped inside the package, not actually the microwave directly. There's other considerations in the packaging. I just got a list here. I'm running out of time, so I'll just read it through. The printing considerations and film color, the machine compatibility in terms of friction or sealing considerations, the clarity and glossiness of the film, the texture, flexible versus crinkly. Sometimes crinkly packages are used on purpose because they give an impression of freshness for products that should be crisp when you eat them. Anti-fog properties, that's the condensation of water that I mentioned. Rigid packages, reclosable packages, and of course recyclability and biodegradability is becoming much more of a consideration. We also have active and intelligent packaging, which has additions to it, like removing ethylene, which is a gas produced by fruits and vegetables that accelerates their aging, so you can absorb that to keep that low. You can also modify the package by having absorbance of oxygen and CO2, desiccants to control the humidity, antimicrobials, aroma release. One of the possibilities is to impregnate the plastic film with aroma of the food product so that when you first open the package, you get an intense experience of that. and then also technology to remotely monitor the package. And there we go. Thank you very much.
Does it ever puzzle you? Have you asked why you seem to fall in love and out again? Do you really ever love or just pretend, oh baby? Why fool yourself? Don't be afraid to help yourself. It's never too late to stop. Look, listen to your heart, hear what it's saying. Stop and look, listen to your heart, hear